All right, team. Sitting here with probably half or a third of the people that we're actually expecting to see here, but that's all right. Um, that's just kind of how it's going right now. All right, we're toward the home stretch at this point. I know a lot of stuff is, if not necessarily slowing down, kind of getting a little bit more grindy than before. But we're in the race to the finish at this point. Don't forget that there is light at the end of the tunnel. You are almost there for a well-earned summer break. Even if you're doing some stuff over the summer, please at least take a week or two to decompress after all of this stuff. But anyways, let's continue the compression. Let's continue all the pressure and everything else, I say gleefully. And again, I know what I do here and everything else. It is part of the situation that we've got on this thing. But if there is ever anything I can do to help with it, please do let me know. Let's talk about standing waves. But first, before even that, let's talk about the stuff that we didn't get to cover too much last time. And what I'm talking about is, well, kind of to do with that informal assignment that I asked all of you guys to do, which was more or less listen. What things do you hear outside, those sirens, those loud vehicles, things moving around? How do you hear the pitch of those things change? I'm fairly certain, if not all of you, most of you know about the Doppler effect in some sort of capacity before we have ever talked about it in this kind of sense. Right? If nothing else, you should be able to hear this pretty quickly and kind of latch on with what you do. Basically, the effect is something like this. Let's imagine something like an ambulance or anything else that has some sort of siren attached to it. How does that thing actually work? Well, most of the time, speakers are essentially cones. And then in the base of that cone is some sort of magnet or some sort of object that's going to oscillate back and forth like this. When it oscillates forward, it compresses the air in front of it. When it oscillates backwards, it refracts the air in front of it. And in that way, we get this series of high pressure, low pressure, high pressure, low pressure. That is what we hear as sound waves, right? Everything that you're hearing right now, even transfers through the microphone and everything else, through your speakers, through your headphones, whatever those are little tiny cones vibrating back and forth, sending out series of high pressure and low pressure, and we hear that as sound. So what happens when that object that's producing the sound begins to move? Well, for the most part, it doesn't really care about what object it came from. Right? Once that high pressure section has been released, it really doesn't care about the object behind it anymore. It has been generated, now it is traveling through the medium with some fixed speed. But what can we do here? If we start to move this object, something changes a little bit. See, whatever this source is that we see in our picture right here, whatever this source is, all of these are essentially our high pressure peaks. Each of these high pressure peaks is traveling outward, and how frequently we hear those high pressure peaks is essentially what pitch the sound is going to be. So for an object moving towards us, what we end up seeing here is that these peaks end up bunching up together. Because once it's been released into the air, it's moving at the same speed kind of regardless. So if this moving speaker is saying high pressure, high pressure, high pressure, all of those peaks are bunching up together. That is, the frequency, as we would be seeing them, is increasing. The wave would look something like this: peak to peak to peak. Whereas if we were someplace behind the object, then we get something like this: peak to peak to peak. The wavelength behind the wave is much longer. The frequency is much lower. We hear a difference in the pitch, whether we are in front of it or behind it, and both of those are different from the actual pitch the object is emitting in the first place. Now, a question for you all, though. If you have taken that assignment seriously, of listen to the outside, see what sounds you can hear, what do you actually hear? What sound do you actually hear? How does the pitch change as that object moves? Any experiences that we're willing to share? Yeah, and so that's a little bit of a different example. That's, I think, going to be a little bit unique how I would hear a lot of the sirens around me. Hopefully that super loud music wasn't myself. I tend to blast my music when I'm driving around, but that's a little bit of a different story. What's going on with something like that is we're very nearly like this picture. As that vehicle is moving right beside us at that point, right? They're not moving towards us or away from us, they're moving parallel to us. So we're not going to hear any sort of difference of the pitch. But as they start moving away from us or towards us, what's going on there is that it's the difference between a radial velocity versus a tangential velocity, right? You as the listener, these are all three-dimensional waves spreading out in one way or another. You as the listener, wherever you are, it depends on how much it's moving towards you or away from you. And that's always a radial component. If you're being circled by a car blasting its bass music, you're not going to hear any sort of distortion or any sort of difference in the pitches. You're going to hear it normal the entire time. But if they start driving away, suddenly you'll hear the pitch shift. Tangential versus radial. So I bring that up because it's one of those things that we might have to consider in a few different scenarios, right? Think about where the observer is. Think about, is this going to be a radial velocity? Is this going to be a tangential velocity? Because if it's only tangential, there's no pitch shift. It's only if the object is moving directly towards or directly away, or that component of that movement, that it's going to affect the pitch that we hear. So two different sets of equations that we need here. Doppler effect for sound, this can be done in one of two different ways. It requires a medium to travel through. So basically, anytime that we're seeing some sort of source, something that is just, this is like a trumpet player laying in the back of a truck just blasting out trumpet, because that sounds like a trumpet player thing to do, if I'm being completely honest. But let's imagine the truck is moving, so the source of the sound is moving to the right. A listener on the right, where the sound is approaching them, is going to hear the pitch shifted upwards, what we call F plus. Somebody away, those peaks are separating out more and more and more, is going to hear a pitch lowered, what we call the F minus. And the equation to find each of these things is almost exactly the same. It's just a little bit weird. It's this, whichever form of this equation you like a little bit better. Basically, if I want to find the plus, then I'm going to take the top half of these things. I know you guys have probably seen plus minus by now, but minus plus is just effectively the exact opposite. So that is to say, if we were to take this thing, if we wanted to find what is the frequency plus, we would take frequency plus is equal to F naught times V of sound minus, you take all the top or all the bottom. You never mix and match these two things. It's a plus minus and it's a minus plus in the equation here. So I'm either doing the plus and the minus or the minus and then the plus, but never plus plus minus minus. Does that make sense? Something like that. If we wanted that plus specifically. Now, this is one such scenario, right? This is the circumstance that the car is moving along the road. However, there are traffic stops on the road, right? I don't know anybody that can consistently get away with blasting through every single intersection without stopping. So sometimes we might be in the circumstance where the source of the sound is stationary, but we as the listener are moving. And in a case like that, the same thing applies. The equation looks a little bit different, but it's still, if you are moving towards the source, you're going to hear a pitch shifted up. Because as you hear those peaks, you moving towards the peaks means your ear catches the peaks faster. You hear a higher pitch. Somebody moving away from the source of the sound, on the other hand, is going to hear those peaks less frequently, hears it as a lower pitch instead. And so the equation is very much in the same way, plus, minus, but now it's the pluses and the minuses actually do go together in this one. So just keep these separate, right? We have two separate sets of equation for the Doppler effect for sound. Either the observer is moving or the source is moving. Whichever it is, you just have to look at what's going on with these things, mess around with it a little bit, find out which one you need to use, plug in the variables you need. Speed of sound, most of the time, not all the time, but most of the time, we are just going to use, again, that 343 meters per second. But not always. And the pitch of the sound depends on the distance between you and the sound. Not quite. It only depends on the velocity. So why is it then that when you hear the car passing you on the road, why does it sound like the pitch shifts depending on where it's at on the road? Why does it sound like the pitch changes as it gets closer and closer and closer? Any guesses? It's not that the sound's frequency is changing, though that is sometimes true. Sirens do change in pitch, so that makes it a little bit harder. But what it is more than anything else, it's the difference between that radial velocity and the tangential velocity. If you are standing some distance away from the road, then the further they are down the road, the more of a radial component their velocity is. As they're passing you, all of their velocity, even if it was the same the entire time, is tangential at that point, and then it goes back into radial. So keep that in mind. It seems like it might change with distance, but that's really only the difference between whether it's moving towards you or whether it's just moving by you. If it's moving towards you, you hear a frequency shift. If it's moving by you, you won't. So, sound, very common three-dimensional wave. Plenty of places that we see this, right? More likely, hear it. But it's not the only type of traveling wave that we're going to consider. Of course, the Doppler effect is another big one. And generally speaking, you may have heard of some of these things before. What do we call it when what are the two names for the Doppler shifts for light? Does anybody know? Redshift and blue shift, that's exactly it. So the question is, which is which? If the source is moving towards you, is that a blue shift or a red shift? If it's moving towards you, it's the blue shift because the frequency goes up, the wavelength goes down. I try to remember the difference between these two. Radio waves can be tens of meters long, hundreds of meters long. X-rays and gamma rays are very, very, very short wavelengths, very high frequency. That's how I try to remember the difference between the two. So going towards blue is a shorter wavelength, a higher frequency. Going towards red is a longer wavelength, a slower frequency. Now, we look up into the night sky. What do we see? We look at all these galaxies. Are they redshifted? Are they blue shifted? Do we have a 50-50 split? What? Does anybody know on this one? So most of the objects in the sky, I think there's only a handful of other ones, and when I say a handful, I mean relative to the number of galaxies we have observed, most objects in the sky relative to us are redshifted. So here's what this looks like. Realistically, if we want to look at what's going on in some sort of other galaxy, we set ourselves up with a very fancy device that can look at all of the different colors, the different frequencies of light that we might see, and plot them out all by their intensity as we see them. There is a really, really, really cool device, a spectrometer, that essentially a prism splits up light, right? Think about the Pink Floyd album cover, that white light comes in, colors come out. It splits it depending on the color of the light or the wavelength of the light. That works for all light, not just the visible light. So what these devices will do is essentially they've got a prism at the start, and then they've got a long set of mirrors. And they will very precisely control. Light comes in, hits the prism, splits. This mirror ever so slightly turns back and forth, and it's essentially taking one wavelength at a time, and then some device at the very end measures that. And where every single one of those things are, they scan this over a very long period of time so they get a very accurate measurement of every single wavelength and how intense it is. Put that off to the side for a minute. Let me come back to that. Atoms like very specific colors. Atoms and molecules both like very specific colors. And I'm talking crazy specific colors. They are always showing up at exactly the same spot and very, very narrow. If you have ever taken any of those, like the spectrum analyzer on the noble gas lamps, right? You plug those things in, they shine off some random colors, you look at them, it splits up all the colors, and you can see that there are very, very specific lines that show up for each of those things, right? And some atoms are even so fancy that they have their name, like hydrogen. The different sets of color lines each have their own name based on who discovered them. What I'm trying to get at here is that when we're looking up into the night sky, when we see all of these colors being emitted, we see dark spots. Essentially, we look at all of the different colors that are out there and we see some slightly darker spots. Those darker spots tell us about what atoms are out there absorbing and scattering that light. And they're always the same, right? The Balmer series of hydrogen is always exactly the same. So we can use that immediately to essentially have a footprint for what atoms are out there. If we're looking around in space, we can immediately use the specific colors that every atom has to, as an identity, as a characteristic. What atoms do we notice out there? Sometimes it takes a little bit of putting together because there's a lot of different atoms there all at once, so we have to be a little bit more careful with it. But for the most part, we can get a very good sense of what different elements are out there just based on what colors they're trying to absorb. Now, with that, we can also know that essentially, all right, well, something like hydrogen, it always has these spacings between those lines. But if we look at that and we notice, hey, this looks a lot like hydrogen, but everything's shifted over by a little bit. Why might that be? Well, the answer is that the galaxy's moving away. All of those wavelengths, the spacing between the wavelengths and their relative positions tells us about what atoms are there. How far away they are from what we see on Earth tells us about how fast that galaxy is moving relative to us. We see most of the galaxy is in a redshift relative to us. We have done all of these identities looking at every single object in the sky. Not every object, but a lot of them up in the sky. We have essentially mapped out what atoms do we expect to see there, how far away from their correct value do we see them. That tells us how fast they're moving relative to us. Space is expanding. Everything is moving away from us, save for a handful of galaxies. There's a lot of clever science that goes into this, right? And atoms are really, really cool because they are so incredibly specific about these colors that they like to see. So, a long-winded way of contextualizing some of these things. Which color shift represents which is moving? If we see an increase in the wavelength, so just as the same way we saw with this one, right? Increase of frequency, increase of wavelength, as we might see these things. If it's approaching, that's an increase in frequency, frequency plus, lambda minus. If it's receding, that's a frequency going down, a wavelength increasing. This over here is our redshift. And then on the other end of this, we have our blue shift. So there's all sorts of crazy cool things that happen out in space and all sorts of these different pieces coming together to build up our understanding of what's actually going on out there. Now, what you actually see in this equation right here, very similar scenario for what we saw with sound, right? So if it's the minus on top, we use whatever's on top the entire way through. If we're looking for lambda minus, we use the pluses. Well, the plus on this one, the minus on this one. If you're looking at the bottom, then it would be plus, minus, plus. So be watching out for that one. And then, of course, this c right here is the speed of light. 3 times 10 to the 8th meters per second. Arguably the most important speed in the universe. And light's a little bit strange because it moves at a constant speed kind of regardless of people. So we get this slightly strange thing. But let's try this in a problem. An extrasolar planet is just a fancy name that says a planet that is not in our solar system. So if we're looking at some distant star thousands of light years away, and we want to try to figure out, are there any planets orbiting around that star? Sometimes we get extremely lucky. Sometimes we get extremely lucky, and that planet will occasionally pass in front of the star, and we see a little dark dot moving across it. And if we see that consistently in a pattern, a periodic kind of movement in front of that star, we can say, hey, that must be a planet, right? Or something, a moon perhaps, or whatever it might be. We can see that object, and we get a sense of where that object is. However, that is only in the circumstance that its plane of orbit, how it orbits, actually kind of pass through with what we're looking up at it. Most of the time, we don't get so lucky. Instead, what we have to rely on is the fact that a planet ever so slightly shifts where a star is moving. And I mean ever so slightly to the point that this star might wobble back and forth 10 meters per second at one peak, 10 meters per second away at the other. It is a very slight movement. It is probably just oscillating around somewhere inside of the star. It's not even going that far from its center of mass. But this does tell us a lot of information about what's going on here, right? We can use this information in all of our old stuff about these circular orbits and all of those details that we talked about in chapter 13 to understand what that planet might look like. But first, we have to figure out what this speed is. And to do that, we need to measure the wavelength that it would be putting out. So what I want you to do for this problem, I want to say, okay, let's imagine the star is emitting some wavelength lambda naught. If this star had been moving at its maximum 10 meters per second towards us, 10 meters per second away from us, how much of a shift in that wavelength would we expect to see for both that approaching, that receding? I want you to take the next 4 or 5 minutes to work on this one, and then we'll come back together and see what you got. All right, so how many people their calculators are giving them maybe feels like a little bit of lip? You're trying to take some sort of square root and your calculator's like, nah, this is 1. Anybody running into that issue quite yet? Hopefully not, but we are getting to strange enough numbers that we're getting close. Hopefully you're not having that issue quite yet, but it will be coming up, certainly if not right now, then when you're taking the end of 192. It's a little bit more of an issue when we're actually dealing with general relativity. We see the same kind of ratio again, V over C, but it's squared at that point, and then you add a 1 to it. Your calculator is going to be upset. Your calculator is going to try and feed you some nonsense that this thing that is clearly not 1 is equal to 1. But let's at least draw out our problem here first, and then we can talk our way through how to deal with something like that. So I just want to kind of draw this thing out to get a sense. I know we had a pretty decent picture already, but for the sake of drawing things, let's go ahead and imagine we've got that. We've got that. We said it's moving towards us in one case. It's moving away from us in another case. In both cases, the speed of that is just a very tiny 10 meters per second. And then we're out here way far away. Not drawn to scale, clearly. Way far away from this. Let me go ahead and move myself before I get any further. Way far away from this is what we're seeing. So this thing is constantly emitting some light at a wavelength lambda naught, but what we actually see gets Doppler shifted ever so slightly. Let's look at the two different cases. Let's start in the case that it's receding, that it's redshifted. In this case, here's what we end up with. Our receding frequency, or rather our receding wavelength, lambda minus. So if I'm taking the minus, then I'm taking essentially everything on that side from my equation. Let me go back to that equation real fast. Let me specify what I mean here. I'm taking the minus, so I'm taking the top function. That means on top, it's going to be 1 plus v of c. On bottom, it's going to be 1 minus v over c. Lambda naught times the square root 1 plus v over c divided by 1 minus v over c. Okay. So again, hopefully, with our velocity as it is, the velocity that we're seeing with this thing is 10 meters per second. The speed of light is 3 times 10 to the 8th. If your calculator can do this, that is fantastic. If it is trying to tell you that whatever's inside of this square root is just equal to 1, we have to take a slightly different approach to deal with this. And that approach is what we call the binomial approximation. This is one of those useful little things as you need it. This is basically saying something like this. If we see some type of function, 1 plus a number x, and all of that to the alpha power. If x is small, x, alpha are small, and that's basically saying more emphasis on x. Alpha needs to not be huge, but more emphasis on x than on alpha. Then this is approximately equal to 1 plus alpha times x. Basically, as long as you see that that x is small, 1 plus something, if that something is small, then you can use the binomial approximation. So what does that look like when we actually apply it here? In this case, I've got the square root of 1 plus v over c. 10 divided by 10 to the 8th that's pretty small. That counts. This is to the 1/2 power. And then I've also got 1 minus v over c to the 1/2 power. These things are going to become something like this. 1 plus v over 2c, approximately equal to 1 minus v over 2c. This just makes this a little bit easier for your calculator to handle, if your calculator is not so comfortable with the original function. Maybe not something that we need to deal with quite yet. Hopefully, your calculator can handle these numbers, but just in case it can't, these are some ways that we can take it that this is very accurate as far as it goes. This will get you really close to the correct number. But anyways, when we do something like that, here's what we end up finding. Lambda minus is going to be equal to, of course, the initial thing, times, here's what I mean when our calculator might not be happy. This is 1.000000033. Calculators don't like to keep track of this many bits, or it's pushing the limits at a certain point. If you've got a really fancy calculator, then you're probably safe from these things. But if you've got a little bit of an older one, we start to get in dangerous territory. But that shift is tiny, right? And this is why, for the most part, when you're looking around, even if you're looking at objects, you don't recognize this kind of color shift. This is not enough of a color shift for your eyes to really pick up on. It is getting close to the amount of color shift that an atom does care about, though, which is kind of crazy when you start to think about it like that an atom is so precise that a shift like this is enough to make it a bit more unhappy with this wavelength that it sees. I mean, atoms are very precise about what colors they like. If you have slightly off from that resonant frequency, then it just does not care about that light anymore. It just passes right on by. So let's go ahead and take the approaching case. And this is the case that is blue shifted. So let's go ahead and do this all in blue. In the approaching case, we've got lambda plus is equal to lambda minus. So again, if I go back to that function, I am taking now everything on the bottom of our plus minus or minus plus. That is, the top now is going to be 1 minus v over c. The bottom, 1 plus v over c. Again, if your calculator can handle this, fantastic. If not, use the binomial approximation to parse it a little bit easier. Lambda plus should be something like 0.999, or let me do the lambda naught, times 0.9999997. So 7 nines, then a 7. A very slight difference, again. But a little bit of a difference. And those are our two shifts. Yeah, the plus minus is a little bit strange. Use the check on this thing for more than anything else, right? A red shift means a longer wavelength. A blue shift means a shorter wavelength. That's what we're expecting to see here, because all of the ultraviolet, all of the blue colors have a higher frequency, shorter wavelength. All of the red stuff has a longer wavelength, longer wavelength, slower frequency, whichever word I'm supposed to use for that one. Less frequency. Okay, so let's go ahead and keep chugging right along here. On to our chapter 17 stuff. And this is where some of our stuff gets a little bit fancy. So there's this concept that we call superposition. And superposition, if we kind of break this apart, what does that word actually mean? The super part of this literally just means overlapping, on top of each other, super to each other. So this shows up in a lot of different circumstances where we have collisions, and not like our old collisions, because our old collisions were particles. In the case of particles, they collide, they bounce off, they're doing their own thing. Waves, on the other hand, they're collisions don't really impact each other in the same way. In fact, the way that collisions work with waves is that they really just kind of pass on by each other. But each wave is going to be contributing its own piece of the displacement. So let's look at it like this. What we've got going on with our red, blue, purple wave here. Notice that the heights are different. And that's a really important factor here. The red wave is traveling to the right, the blue wave is traveling to the left. When they combine in the middle, the peak is larger than any or either individual wave because their displacement of the string, those displacements are being summed up together. It is the superposition of those two waves. We also have this thing up here that's showing what happens when we have two waves that collide and what that looks like, their superposition as a function of time. So the red waves on top are essentially what each wave would look like if nothing was in the way. An up wave and a down wave, when they combine together, we get this wonky shape in the middle as their displacements sum up together. So we have special circumstances of these superpositions. So on its own already, that's what's going to happen anytime I've got waves that are moving through the same area. They will superimpose themselves. They will add up together and then they'll keep moving on their own way. They don't actually collide in the same way. We just briefly get an effect of what it looks like to see both of their displacements active at the same time. But on strings, we can get something a little bit more interesting going on. See, if you've been working with some of these simulations so far, you might have noticed that when a wave that is traveling along a string hits some sort of obstacle, there's a reflection. Right? And that reflection depends on what kind of obstacle it is. If it's just a harder part of the string or a thicker part of the string or anything else, some of it will still keep going, some of it's going to get reflected back. If it is a hard stop, if something pins it in place, in a case like that, then all of it is going to be reflected. But that means that we can get essentially, if I pluck a string that is fixed at either end, then I can get a right traveling wave and a left traveling wave because they're both going to just be kind of constantly bouncing back and forth like this. Then we just do our superposition. Superposition is just essentially taking the displacement function of each one and adding them up together. The result for this is this function down here, which is really, really, really unique, but it might not appear so at first. But let's pick this apart. We had from before sine kx minus omega t, so that is to say where the peaks are at, where the valleys are at, that depends on both space and time. Every spot is eventually going to hit a peak at a certain time, but we just kind of have to agree with those set. We have to deal with both of those variables, but every spot along the string at some point will see a peak. Same deal with the left wave, but now it's a plus omega t instead. When we combine these two things together, we can simplify these functions down a little bit. And when we simplify them down, we end up splitting apart our kx and our omega t. And this has some unique implications, because what this is saying here is that this sign of kx, this does not depend on time. That is, where we are at on the string, not every part of the string is going to be able to go to a maximum amplitude anymore. Cosine of omega t says what is allowed to go to an amplitude is just going to depend on time, no longer on space. And we get what we see here on the right. So we have our right traveling wave, our left traveling wave, and then the superposition of both of those. What we call a standing wave. And it gets the name standing wave because basically what it looks like is that it's just a wave going up and down and up and down in place. It doesn't look like it's moving anymore. And what we see, of course, the big wave, if we were to pause it, and can I actually pause this thing? Will it allow me to pause? If I pause it, and let me wait for just one more cycle through, like that. What we see right here, that's a sine wave, right? Can we all agree with that? That is my 2a sine of kx. But it keeps oscillating back and forth in that exact same spot, combined with the cosine. That's why we see this sine wave increasing and decreasing as time goes on. But where those peaks are the same every single time. Light interference is something that comes from this, but we'll talk about that a little bit more coming up. Not quite yet, but light will do a very similar thing because it is another traveling wave. So we've got some terms that we need to talk about here. These terms are nodes and antinodes, first of all. These tell us a lot of information and they reflect very much what we're actually looking at. So a node is essentially any spot that is going to be 0. Any of these spots that it doesn't matter where the wave is at, we're seeing 0, 0, 0, 0, 0. It might oscillate back and forth, but if we even look at some of these spots, sorry, my computer thinks I'm holding down control, and it still thinks I'm holding down control. There we go. This spot right here is an example of a node. We notice that anywhere in this cycle, it never stops being 0. It never goes anywhere. This sine of kx essentially says this spot right here is never going to be anything other than 0. It is a node. An antinode is the exact opposite of that. It is the spot that is most affected by that amplitude. It is the peak that we see of the standing wave. So we've got these combinations of nodes and antinodes. And I wanted to start with this picture. You'll notice I've got one directly behind it, but this picture tells us a neat piece of information about what we're seeing in these oscillations. The nodes show up at factors of 1/2 the wavelength. Remember that a full wave looks something like this, right? That is our full wavelength. We've got the full wave in front of us. There's a node here, there's a node here, there's a node here. At x is equal to 0, at x is equal to halfway through the wavelength, and at x, and I know I'm covering up the beginning of that x, but that says x is equal to 0, and then at x is equal to the full wavelength, we've got another node. The antinodes, where we see the peaks, are a quarter wavelength separated from those, split right in the middle. That is, we see an antinode right here, we see an antinode right here, or a maximum peak at these two spots. Lambda over 4 and 3 lambda over 4. 3/4 of the way over and 1/4 of the way over. But all of these, you'll notice, are separated by half wavelengths. The nodes are all half wavelength away. The antinodes are all half wavelength away from each other. And the other picture behind this one is another interesting one, just because this shows essentially what's going on with that amplitude. Different spots will keep moving a different relative displacement, right? We see a lot of kind of our spring motion going on here, but for a certain spot, it's only allowed a certain amplitude based on that 2a sine of kx. So, apply this to strings. Strings are held fixed at each end of the string. That means we are going to be creating standing waves. Now, what's unique about this is that there's a lot of different vibrations that are allowed. Do you remember when we were dealing with these wave equations and we basically were looking for solutions that work on these strings? What solutions could exist given these initial conditions? And strings are very unique because, well, there's more than one answer. A string is allowed to vibrate in multiple different ways, and sometimes all at the same time. And it just so happens, and this is not just me being the stereotypical guitarist, but it just so happens that I have a string that is fixed at both ends. 6 of them, in fact. At the bottom end right here, at the bridge, the string is held in place. At the top end, the string is held in place. If I pluck it in the middle, we get a sound coming out of it. That is our longest wavelength. That is saying what condition, what type of wave would it work that would have 0 at one end, 0 at the other end, and whatever, anything goes in the middle. The longest wave that would do that is this one right here. Now notice, is that an entire wave? Yes or no? What do we think? Full wave? No. What is it? It's only half of the wave. So the longest wavelength of a wave traveling on a string like this is actually twice the length of the string, because this condition, the fact that it has to be 0 at this end, has to be 0 at this end, and anything goes in the middle, the longest wave that can do that is one where we only see half of the wave on the actual string. The other half is in this imaginary space out here. Now, one of the really cool things about having strings directly in front of me is that I can set specific conditions for it. So if we notice, that is what we call the fundamental. The first harmonic, the fundamental harmonic, essentially the longest wavelength we can have and the lowest frequency. The second harmonic is what happens when we do have the full wavelength on the string, but now essentially the spot in the middle is 0. And with an instrument like this, I can actually instigate that. If I touch my finger directly in the middle of the string, so I've got from the very bottom to the very top, my finger is currently touching right in the middle. I'm instigating the condition, this spot as well has to be 0. 0, 0, 0. When I pluck the string, I get a new sound, a new frequency, double the frequency of the original note. And I can instigate these conditions further down as well. Notice what we see down here in the third harmonic. This is 1/3 of the way over. We have a 0 spot. All of this is on the exact same string. 1/4 of the way over. And we can keep carrying that up and up and up and up and up if we want to. All of those, what I'm doing is I'm saying, let me get this harmonic instead. I put my finger in one specific spot, and I say, this is another added condition. But when we pluck the string as a whole, why does it sound like a guitar? Because when I pluck it like this, all of these sound at the same time. The vibration is much more complex than just a sine wave. In fact, there are very, very few instruments that actually produce just sine waves like this. Disregarding digital instruments like synthesizers, does anybody know what instrument gets closest to a pure sine wave like this? Does anybody know this one? Or have a guess? The two that I think of, the two that are most like a sine wave that I know of are the clarinet and the oboe. They are designed in such a way to get as close as possible to a pure sine wave, but they still don't sound exactly like a sine wave. There are differences in there. There are these extra little modulations. The actual sound that we hear is a superposition of all of these harmonics at once, and our ear picks that up, and it makes one uniform sound out of all of that. So how much, there's of course a lot of complicated things that go into this. How much of each harmonic you hear is a part of the uniqueness of each individual instrument and each individual sound. As I'm making sounds right here, if I were to sing a single pitch, that is not just that single frequency. It is not a sine wave. It's a combination of many different waves superimposed on top of each other to give my voice its own unique sound. Everybody's voice is going to sound different. It's going to be a combination of different waves just like this that produce the unique sounds that we know and listen to every day. So for each of these wavelengths, there's a couple things that we can notice about these, right? So each allowed wavelength has to be some factor based on the length of the string in the first place. Specifically here, each wavelength is 2L divided by M, where M is just some positive integer, right? So what we're seeing here is that for the longest wavelength, we're only getting half of the wavelength, so the longest wavelength is 2 times the length of the string. The second harmonic, we see 1 full wave on there, so that is just L at that point. And then we have 3 wavelengths, so that's going to be, at that point, a 2L over 3 is the wavelength, so on and so forth ad nauseum. We also see a similar kind of pattern follow in with the frequencies, where the frequency is always a multiplicative factor of the fundamental frequency, which is the easier way to write this thing out, but realistically, it's related again to the velocity and the wavelength as we would see them. But basically, every single frequency that you're going to see on a regular string, it's either F1, or 2 times F1, or 3 times F1, or 4 times F1, as you go down and down and down. So, let's try this. And let's wrap in all of these old topics together again, right? Did you think we were done with torque? Did you think we were done with equilibrium problems? Not so. They are still here. They're never going away. Let's imagine, what is the fundamental frequency of this steel wire as we see it roped up in this contraption? I want you to take the next 5 or 6 minutes to work on this one a little bit, and then let's see what we end up with. Okay, let's go ahead and start taking a look here. So here's what I'm thinking. We have a couple different pieces that we're going to need to look for here first before we can get into this, but I want to kind of direct where we're thinking about this thing before anything else. So let's start with this. We're focused on the string, right? Or the wire, rather. We want to know some details about the wire. We want to know what frequency does it actually vibrate at. Move myself down here before I forget. Let's go ahead and say this wire has a length L. And just make everything a little bit easier. So we want to know the frequency of this vibration. What are some details about this? Where does the frequency show up when we're talking about oscillation standing waves on a string? Any good guesses here? I really don't have a ton of them. I mean, I guess in a sense, if I could talk about the period of the oscillation, that's one place, but we don't have any equations that are relating super well to the period in a case like this. What I think is probably the best one to look forward to is something like this. The velocity of the wave on the string is equal to the frequency of that oscillation times the wavelength of that oscillation. So we're focused on the fundamental. So call it F1, call it lambda 1. What is lambda 1? Let's start there. What is lambda 1? Do we have enough information to solve this right out? For the fundamental harmonic, the wavelength on this specific string, or wire, again, sorry, is what? Any guesses here? I'm going to think 2L. Because again, let me think about what is the largest wave that can exist on this wire. This is pinned. This is pinned. My biggest wave looks something like this. Half of the wavelength, Not the entire thing. There's some virtual portion of the wavelength way over here. But what we're expecting to see then is that the largest wavelength, lambda 1, is equal to 2 times L. Now, quick question. Is L something that I know? Well, looking at this thing, I've got this side of the triangle. I've got the angle of the triangle. I feel confident that I can find L. Let's leave that for later. Let's just say for now, we feel pretty confident that we can find L. Treat that as something that we actually know for now. We'll come back to that in just a little bit here. Okay, so we have handled the wavelength. We know what the wavelength is supposed to be. What about the velocity? Where does that come from? Do we actually know that value right off? Or is it something that we have to solve? Is it something that we look up in a table? Does anybody have any suggestions for me on that one? What things does it relate to? Can I just plug in 343 or no? My sense here, 343 is specifically the speed of sound in regular atmospheric air. The speed along this wave does not care about the 343 of the air around it. That is a very different kind of ballgame at that point. What we're looking at is what is the speed along this wire. Speed along wire. Exactly. It depends on the tension and the linear mass density. If we remember this equation right here, it's that velocity on any string, wire, anything else like that is equal to tension divided by linear mass density, square root of that combo. Okay. Another quick question. Do we know anything about the linear mass density? That one's a little bit easier in this case because I do know the length and then I know what the mass of the wire is. So I feel pretty confident in just saying right off the bat, mu is equal to the mass of the wire divided by the length of the wire. So I feel confident in knowing mu, but I don't know tension. And tension's going to be a little bit more tricky. So here's what we need to do. We need to take a closer look at this thing. We need to see where tension is pulling, what it might be doing. Tension will pull something. Oh, that was not a very straight line. It's that some of these angles that I can't draw pretty well. So my tension, I expect to point something like this. What other forces do I have? Acting, let me focus in on the beam because that's where everything is attached. I've got right smack dab in the middle. Let me call some things here. Let me say that the bar or the beam has a mass, say capital M. Let me say the block has a mass lowercase m, just so I've got some variable names in here. So this force would be, in blue please. Thank you. Capital Mg. I'd see a force here, lowercase mg. What about the force from the wall? What about right here? What is that going to look like? Do I know anything about that force right there? Oh, it's a mystery force again. I don't like this mystery force because I don't know the tension. And if I'm thinking about this mystery force, I know certainly it's going to have a positive x component, and it's probably going to have a positive y component, or else the bottom would just kind of swing out to the outside, kind of like this. So, I don't know what it is, though. And the fact of the matter is, if I need to solve it, I will, I guess. But because it's a mystery force, because I don't know anything about it, I want to make that a pivot point. See, looking at this bar, we might remember, in equilibrium, if this thing is not swinging, if it's not collapsing, if no wires are snapping or anything else like that, two details that are very important. The net force in both x and in y is 0. The net torque is also going to be 0. Let me focus in on that torque, because again, mystery force spooks me a little bit. If I focus in on the torque, what do we see? Well, from my mystery pivot, I have 3 different torques that are going to be acting. I have my capital Mg acting right smack dab in the middle. So that is 1 meter away, magnitude, capital MG, sine of 90 degrees is just going to be 1, so I don't need to worry about that. Now, positive or negative is the question here. And I see this thing is trying to spin me clockwise. Clockwise gives me a negative. Okay? Then I also look at lowercase mg. That's now a full 2 meters away, similar direction. Lowercase mg, again, sine of 90, no need to worry about it. The last thing that I've got is my tension, acting similarly, 2 meters away, tension, but it is acting at an angle, so that will be a sine of 45, but it is the only one trying to spin me counterclockwise, so that gets a positive. Now I look at this thing and I say, okay, capital M is 4 kilograms, lowercase m is 8 kilograms, sine of 45 is a number, g is 9.8. I have everything I need in that equation right there. The only thing that I don't know is tension, so I can move the things to the other side. This divided by 2, sine of 45, gives me my tension. My tension in that wire is something right around, what, 138.6 newtons. Pause. Isn't there a mass of the wire? Should that be something that we consider here? What do we think? Why might I consider it? Why might I not consider it? Do we have any guesses? I mean, I think we can all agree it's easier if I don't have to. I would have a much better time if I didn't have to consider that. I would probably be in a better place. But it probably doesn't have a huge effect on tension, because let's think about this. The tension in this wire, 138.6 newtons. How much force is gravity going to be contributing here? Something along the order of 0.075 times 9.8. So at the end of the day, even if we kind of approximate that up to 10, say it's like 0.75, it is still less than 1% of the tension, comparatively. I'm going to say, in any sort of force balancing or anything else like that, this less than 1% impact, if I round a number somewhere, it's probably going to have a more significant impact than if I were to actually consider the mass of the wire. Now, we're not dealing with large wires here. If this was a 5 kilogram wire, then I would certainly be thinking about this a little bit more. I would certainly consider, hey, there's going to be some sag in the middle of the wire. There's some extra forces going on here. There's some more details than what I'm actually considering. But in a case like this, because it would have such an incredibly small impact if I were to try to consider it, I'm going to say it's best left kind of left over to the side. Now, if you go into a more rigorous classical mechanics course, this might be a place where you actually have to consider it, right? It will become a pretty important thing. If you're building bridges or anything else like that, where you similarly have wires that might be oscillating in some way or another, but have a reasonable mass that they are actually impactful in the rest of the equation, you'll have to consider this. But for right now, we want to focus in on the concepts more than anything else. This impact is too small for us to really care about. That's a problem for a 400 level class if you are going to end up going into one of those. So now at this point, we have our tension, 138.6 newtons. It's probably a good time to find L, right? One of the things that I can do here is I can say, hey, this is a 45, 45, 90 right triangle. So I know that this vertical side is 2 meters. Pythagorean's theorem would tell us that this length L is 2.828 meters. Or you can do 2 meters divided by cosine of 45. Gets you the exact same number either way. With L in hand, we can keep moving right along. We can say, all right, then the mass density is something like 0.0265 kilograms per meter. we can say something like the wavelength is realistically just 2 times the L value. And what we would find for the velocity, if we are to actually plug in a lot of these values, the velocity would be something along the order of 72.38 meters per second. All of these things thrown together, when you combine them, what we know to be lambda 1, what we have now found is the tension, mu, the velocity, all of those values summed up together. At the very end of the day, we should plug all those numbers into the fundamental frequency to find 12.79 hertz. So pretty slow oscillation when you consider stuff like sound. It's below our hearing, but it would still, visibly buzz around a little bit if somebody were to pluck it. So as it turns out, strings, wires, they're not the only things that can vibrate like this. In fact, you can get standing waves in a lot of different things. Two of the most common, for you guys at least, are going to be essentially tubes, and then lasers are another fantastic example of this. I know there's some examples in the book of standing waves as well, but lasers are a fantastic example, and they're very, very cool, because what goes on with that is you have some sort of lazy medium in the middle. On one end, you have a very reflective mirror. On the other hand, you have a pretty reflective mirror. And the very reflective mirror always reflects the light back in. The light keeps bouncing back and forth, and all of the light is very, very, very uniform altogether. The kind of reflective mirror lets some of the light leak out the other side, and that's why we get laser light that is so exactly finite. All of the light is supposed to be the same, and it behaves a little bit differently than like your normal flashlight. But you might have also seen this in a number of different places, like, again, instruments. All sorts of woodwind instruments are essentially tubes that have standing waves inside of them. If you have ever played a woodwind instrument and you have noticed what is the difference between playing a low note and the high note, right? The difference between the octaves is essentially just how hard you're blowing. And that's kind of an assumption on that. But basically what we're saying here is that, again, there are multiple different harmonics allowed to exist in these tubes. So for all of these things, when we're doing it with a tube, it's a little bit different. It's not quite the string anymore, but at the end of the day, it looks very similar. For a tube closed on either end, we get similar kind of structures of one end is going to be 0, it's pinned in place. The other end is going to be 0, it's pinned in place. And whatever satisfies that is allowed to oscillate inside of the tube. We also get this kind of strange thing where we have high pressure on one side, high pressure on the other side, and anything that's allowed inside of that is allowed to go as well. That is, again, if you are essentially blowing into a reed or blowing into a mouthpiece, you are creating high pressure at that end. And then you get this standing wave throughout the rest of the instrument that puts sound out. So in this case, we're dealing with a second harmonic, right? Because we see 2 antinodes, not the full stretch over the entire thing, but any different combination that would satisfy those conditions is allowed to exist. So, totally tubular. There are 3 different combinations of tubes that we might see. We could see a closed tube, exactly what we just saw. And what we would see, the wavelength, it would behave just like a string would. Either end would have to be 0. Right in the middle, you can get the maximum displacement of the air, or 0 pressure at that point. And again, you can have these generated harmonics going all the way down. So we've got our fundamental harmonic, we have our second harmonic, we have our third harmonic. If we have an open tube, which is a little bit different, but if you have an open tube, we get something that is kind of exactly the opposite of what we have just seen with the closed. Now, instead of having the largest displacement be in the middle, it's just on the outsides. That is, anywhere it's on the outside, we have no pressure, we have maximum displacement. So everything has been kind of like shifted over by a quarter of a wave. Now the node is in the direct middle instead of being one on each outside, and everywhere there was an antinode before, it's been replaced with a node. But at the end of the day, it behaves very, very similarly to our closed tube. And so both of these, I want to draw kind of like there's a big column between these two, because the closed and the open behave very similarly. They give a very, very similar kind of shape, band structure, the harmonics, all of that good stuff are described by the exact same equations. The open-closed is unique in this, because on one end, we see, okay, well, there has to be zero pressure because it's closed. On the other end, or it has to be maximized pressure on one end, it has to be zero pressure on the other end. And so what we get in this case is not a half wavelength kind of structure, but a quarter wavelength kind of structure. What conditions satisfy these two bounds? And this is a little bit unique. So now what we're getting is kind of like a quarter of a wavelength, and then 3/4 of a wavelength, and then 5/4 of a wavelength. It keeps going up by a little bit of a strange structure in this one. So the open-closed is a very unique circumstance, but this is actually a lot more like what a lot of our wind instruments are, right? Clarinet's a fantastic example. One end is closed, that's where the reed is. The other end is open, the bell. Trumpets, tubas, flutes, piccolos, all of those wind instruments are essentially in some sort of open-closed scenario. So, feeling good about all of this stuff, hopefully. Now, I'm not going to try and play this one right now because realistically, even had my internet not been garbage today, I still feel like this one doesn't translate nearly as well. What I do highly recommend, go download these slides, go watch this video. It's a short little thing, but what's going on essentially, and I can skip to somewhere in the middle of the video, we've got a tube with a speaker at one end and filled with propane and lit on fire. And when you put sound through it, you get changing shapes. And it follows, essentially, all of these waves that we're seeing right here. So, please, check it out. It's got some sound and everything else. There are a few flashing lights because, as you can probably tell, there's flashing fire in different spots. So, for anyone that's sensitive to that, just be careful. They're not too intense, but there are some flashing lights. So, let's try a problem with this idea. This thing right here, we've got a piston on one end, or a speaker, and the other end is closed. What type of tube is this? Is this closed, closed, open, 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 closed? What do we think? What is the piston doing to this? Okay, so one end is obviously closed. It's not an open, open. But is this an open, closed, or a closed, closed? Any guesses? So if the piston was not moving at all, it is still filling up the gap. If we'd taken the piston out, if we took this speaker out, then I would agree we've got an open, closed kind of tube. But we have essentially inserted this piston in that sits exactly flush with the rest of the tube. It closes that end off. So in a case like this, what we are looking at is a closed tube. Now, we're using this to essentially measure what is the speed of oxygen. What is the speed of sound in oxygen? We have set a bunch of fine dust particles in this tube, and we have put a 400 hertz frequency into it, and we notice the little tiny piles that keep popping up in these areas. We measure the distance between some of these piles to be 123 centimeters. What is the speed of sound in oxygen given all of this information? Take the next 3 or 4 minutes, work on this one, see what you can come up with, and then we're going to talk about it together. Okay, so let's talk about what we've got. What I'm seeing right here, the locations of each of these little tiny piles of cork, they're corresponding with where the displacement is 0. Right? Notice that in each of these corners, we see a little tiny pile right here. We see a little tiny pile right here. That is telling us that everywhere there's a little tiny pile of cork, there is 0 displacement. So right here, 0, 0, 0, 0, 0, and 0. What type of wave can exist in this? Well, it looks like this. Every dot has to be a 0. My standing wave looks something like this. So then, which harmonic are we in? Which harmonic do we actually have with us right here? Guesses? Fifth harmonic. We see 1, 2, 3, 4, 5 antinodes. We are in the fifth harmonic. So what I'm going to do with that is I'm going to label this little tiny thing. F5 is 400 hertz. Now, the other thing that I need to do is I need to look, okay, well, what is the wavelength that I actually have in my hands here? What does this 123 actually relate to? And if I'm counting the distance between these two, what I can say is I have 1/2 of a wavelength, 2/2 of a wavelength, 3/2 of a wavelength is equal to 123 centimeters. 3/2 of a wavelength is equal to 123. So the wavelength of this, wavelength 5, is equal to 82 centimeters. Then the last thing we need to do, we're looking for the velocity. Velocity is equal to frequency times wavelength. Plug those two in together, and what we should find is something along the lines of 328 meters per second. Compare it to the speed of sound in regular air, 343. Oxygen makes up about 20% of the atmosphere. Nitrogen, very similar to oxygen, makes up a large majority of it after that. I think 65% or something like that. So the fact that oxygen looks pretty similar to the regular speed of sound of air, that sounds pretty reasonable to me. I think I'm happy with this answer. All right, team. Well, instead of an in-class today, I've got just a small little thing on mastering to play around with this a little bit to see these effects of superposition for yourself. And then there's a little bit more of an involved lab to go with it as well. So, but that's all your stuff on this one. Next time, we'll close out this chapter, and I think next time will be a little bit more exciting. I want to demonstrate a few of these concepts just a little bit more before we get into it all the way. So I think I'm going to bust out my amp and oscilloscope, and we can see how some of these waves appear on the oscilloscope to really kind of show what I'm talking about with a lot of these different waves being generated. But that'll be for next time. So until then, team, thanks for being here. I, of course, always appreciate it. I'll see you guys again next time.